$60 billion. That's the staggering amount of global investment poured into nuclear energy just in the year 2023, a massive 50% surge from just 3 years prior.
But hold on a second. 404. Despite that massive influx of capital, as of January 1st, 2026, there are only 404 operational commercial reactors on the planet, which is actually a net drop of 5 units from the year before.
It's the ultimate unaddressed contradiction at the heart of modern energy. We're seeing soaring capital investment, and nuclear power is constantly hailed as our ultimate climate savior. Yet, global operational capacity, it remains virtually flat at 369 gigawatts.
Welcome back to Learning with Pratik. If you're new here, I try to increase neuroplasticity by exploring a new topic every day. I do all the reading and researching, so you don't have to. Today, we're unpacking the true state of the global nuclear industry, the technology, the economics, and the deeply complex legacy it leaves behind. So, let's dive into this. Chapter 1. The Nuclear Contradiction. All right, we need to start with a grounded reality check of where the industry actually stands right now, stripping away all the theoretical rhetoric. When you look closely at the data, the global reality is incredibly asymmetrical. Right now, there are 63 reactors currently under construction worldwide, and those are expected to generate over 70 gigawatts of power. But here is the critical detail. 69% of the construction starts over the last few years were driven entirely by China. In stark contrast, there is literally zero commercial reactor construction underway right now on the entire American continent. In the EU, the only unit being built is one that originally started construction way back in 1985. The fundamental growth of nuclear power is shifting completely to the east, dominated by Chinese and Russian state-backed enterprises, while Western capacity just stagnates. And the reason for the shift is deeply systemic. Western projects usually suffer from a loss of institutional knowledge, intense regulatory hurdles, and totally fragmented supply chains, basically turning every new reactor into a bespoke, over-budget mega project. Meanwhile, China has successfully leveraged state financing to standardize their designs. They're essentially building reactor components on a predictable, continuous assembly line.
Chapter 2. Anatomy of a reactor.
To understand why building these plants in the West has become so incredibly complex, heavily regulated, and capital-intensive, we need to ground ourselves in how established nuclear infrastructure actually works. Now, the vast majority of the world's current fleet relies on the pressurized water reactor, or PWR. This is a dual-cycle nuclear generating system. Its entire architectural philosophy is designed around one core objective: isolating radioactive materials from the power conversion process. Take a second to consider that dual-cycle concept, because it's absolutely the foundational bedrock of modern nuclear safety. This setup brilliantly illustrates how that isolation is achieved. A PWR uses 2 distinct closed loops. First, you have the primary cycle. This contains the reactor vessel, the pressurizer, and the reactor coolant, which is just pure water mixed with boric acid. This water gets heated to over 500 degrees Fahrenheit by nuclear fission, but it's kept from boiling by immense pressure. Crucially, this primary cycle is located entirely inside a containment building. And when we say containment, we are talking about staggering physical scale. Think walls of high-density reinforced concrete up to 4 feet thick, lined with thick steel, and built to stringent seismic standards, literally capable of withstanding a direct impact from a commercial airliner. The intense heat is then transferred through heat exchanger to a completely separate secondary cycle. This secondary cycle contains the steam system and the turbines that actually spin and generate the electricity. Because the 2 cycles are physically sealed out from one another, that high-temperature radioactive coolant never actually reaches the turbine building. It drastically minimizes environmental risk, protects the plant personnel, and frankly, justifies those massive upfront construction costs.
Chapter 3. The Zero Carbon Promise. So, if these facilities are so mechanically complex and wildly expensive to build, why the massive recent surge in investment? Well, notice the sheer scale of the emissions delta in the data here. When we analyze the complete life cycle greenhouse gas emissions of various electricity generation technologies, and yes, that includes mining the uranium, the concrete-heavy construction, decades of operation, and final decommissioning, nuclear still sits right at the absolute bottom of the pack. It ranks right alongside onshore wind and run-of-river hydro. We're talking almost 0 grams of CO2 equivalent per kilowatt hour. That's a night and day difference compared to unabated natural gas or coal. It is a highly potent, exceptionally clean baseload power source that operates whether the sun is shining or the wind is blowing. But the modern economic argument for nuclear goes way beyond just putting clean electricity onto the grid. Nuclear power provides 24/7 continuous electricity and industrial-grade heat. And this continuous output is absolutely crucial for efficiently producing low-carbon hydrogen. Right now, nearly 75% of the world's hydrogen comes from unabated natural gas. By using nuclear power to produce clean hydrogen instead, facilities can create a highly valuable alternative revenue stream. More importantly, this clean hydrogen is a vital tool for decarbonizing hard-to-abate sectors. Take steel manufacturing, for example. A traditional steel plant consumes millions of tons of metallurgical coal, making the steel industry alone responsible for roughly 8% of total global CO2 emissions. You can't exactly run a massive heat-intensive blast furnace on variable energy sources like solar or wind. But if we replace that coal with clean hydrogen generated by a steady, round-the-clock nuclear plant, we can genuinely begin to decarbonize the heaviest, most stubborn pillars of our global economy.
Chapter 4. Generation IV Claims.
This urgent need for clean, reliable energy has naturally spurred immense interest in the theoretical future of the industry. The Generation 4 International Forum, or GIF, has outlined some pretty utopian goals for the next era of nuclear power. We're talking enhanced safety, less radioactive waste, economic competitiveness, and proliferation resistance. But when we place that promise next to the commercial reality, a much different, far more sobering picture emerges. Looking historically, 14 experimental reactors that fit the Generation 4 profile were built between the 1950s and 2010. Today, every single one of them has been shut down or decommissioned. They currently hold absolutely zero competitive foothold in the global market. In fact, there are only 3 commercial units operating today that technically classify under these new technologies, located in Russia and China, and independent analysis shows they actually fall significantly short of those core Generation 4 goals.
The crucial thing to understand here is that the term Generation 4 itself is actually kind of misleading. It implies a seamless, continuous evolutionary upgrade from our current Generation 3 light water reactors. But in reality, these are mostly early, unproven prototypes. We're talking about concepts based on fundamentally different physics, things like using molten salt coolants or operating on fast neutron spectrums. While the basic principles of these technologies have been understood in laboratory settings for decades, they simply lack technical maturity. And in nuclear engineering, scaling up really matters. You have to figure out exactly how entirely new materials are going to react to intense radiation and highly corrosive molten salts over a lifespan of 40 years. Generation 4 simply lacks the decades of operational refinement, rigorous testing, and hard safety data that completely characterize our conventional reactor fleet.
Chapter 5. The Multi-Generational Legacy.
And that technical maturity matters deeply, because the consequences of this technology outlast us all by orders of magnitude. We have to be honest about the immense timescales required to manage the life cycle of nuclear power. Just look at the painstakingly slow, highly technical process of decommissioning the Fukushima Daiichi plant after the 2011 disaster. This is a multi-decade roadmap. In 2020, they finally managed to reduce contaminated water generation to 150 cubic meters per day. Just recently, in January 2026, they completed the installation of a massive cover on Unit 1, using custom robotics because radiation levels there are still fatal to humans. By June of 2026, they started fuel removal from Unit 2. Their target to simply complete fuel removal from all the units isn't even until 2031. And remember, that's just the roadmap for a single, albeit highly complex, site. Beyond decommissioning, there is the permanent, unavoidable issue of spent nuclear fuel. Let's read this consensus quote from the American Nuclear Society carefully. Safe and technically feasible deep geologic repositories are the preferred means of protecting people and the environment in the very long term. To manage highly radioactive, long-lived isotopes, we must isolate them. The strategy is to embed them deep underground in incredibly stable, engineered geologic rock formations, like salt beds or granite that haven't shifted in millions of years. This repository must be passively safe, meaning once it's sealed, it cannot rely on the ongoing care of institutions, maintenance crews, or even systems of government. Think about it. 100,000 years ago, humans were just starting to wear clothes. Now we have to engineer a warning system that will still make sense to whatever is walking the Earth 100 millennia from now. Because let's face it, human governments simply do not persist into the distant future.
And see how this builds directly into the concept of intergenerational equity? Those of us benefiting from nuclear technologies today must act responsibly to avoid passing unreasonable risks and massive financial burdens to future generations. Siting and licensing these deep geologic repositories can take decades, and it often requires complex political resets. Germany, for instance, completely phased out its nuclear program post-Fukushima, leaving behind a massive logistical puzzle for its waste. Japan faces a dense population and high seismic activity, heavily complicating their site selection. And over in the United States, billions were spent on the Yuck Mountain repository, only for shifting political administrations to completely halt the project. It just proves that human politics are far more volatile than the radioactive half-lives we're trying to manage. But despite these geopolitical hurdles, developing permanent, passively safe repositories isn't just some infrastructure challenge, it is a fundamental moral obligation.
Which brings us to the ultimate paradox of our modern energy landscape. How do we balance the urgent, immediate climate need for massive amounts of zero-carbon baseload energy with the sobering 100,000-year legacy of nuclear waste? It's a question with no easy answers, but one we absolutely must collectively solve. Let me know your thoughts in the comments below, especially if you have something particular in mind. Thanks for watching. Tomorrow we open a different page. Until then, Pratik, out.